Hey everyone, so glad you're here. In today's explainer, we're diving into something super fascinating, the hidden software architecture that literally brings physical AI robots to life. We're going to unpack how two completely different software pipelines give these machines the power of human-like speech. It's kind of like a tale of two distinct approaches, right? And by the end of this, you'll see exactly how the physical hardware and what we actually want the robot to do totally dictates the code we write. Let's get into it. Quick look at our roadmap for this explainer. We'll start with the big picture, making AI robots talk. Then, we'll establish a baseline, looking at the OpenDuck's turn-based pipeline. From there, we'll crank up the speed with the Mini-Pupper's real-time streaming approach, put the two head-to-head, and wrap up with our core architectural takeaway.
All right, Section 1, making AI robots talk. We're bridging the gap between silent hardware and intelligent conversation.
So, what's the core magic we're trying to pull off here? Well, traditionally, hardware robotics rely on these super rigid, script-based interactions. It's pretty clunky. But by using the Audio AI chat framework, our goal is to transform these traditionally silent machines into highly responsive, conversational companions. And honestly, this is absolutely crucial for the future of robotics. To make this happen, we're relying heavily on large language models, LLMs, to power this seamless voice-to-voice loop.
But here's the thing you got to keep in mind. Not all robots are created equal. These two platforms have entirely different physical brains and operating systems. The OpenDuck Mini V2 is rocking a Raspberry Pi 5 with the Bookworm OS, running a turn-based pipeline. Meanwhile, the Mini-Pupper 2 uses a Raspberry Pi 4B running Ubuntu, which is specifically tailored for a real-time streaming pipeline. This hardware divergence, it totally sets the stage for their contrasting software architectures.
Moving right along to Section 2, OpenDuck's turn-based design. This one is all about being sequential, reliable, and straightforward.
Okay, let's look at how this actually builds a highly logical, sequential pipeline. The OpenDuck takes a very deliberate, linear approach to problem solving. It's a step-by-step thing. First, it records audio using an energy-based voice activity detection, or VAD. Then it transcribes that audio to text using speech-to-text. Next, it shoots that text over to an LLM to generate a chat response. And finally, it uses text-to-speech to actually speak the response out loud. It's literally exactly like a walkie-talkie conversation. Stage 1 has to completely finish before Stage 2 can even think about starting. Now, you might be wondering, why do it this way? Well, what makes this so brilliant for the OpenDuck platform is the rock-solid stability. I mean, anyone who has ever wrestled with complex C-based Python audio libraries knows it can be an absolute nightmare. A real headache, right? So by avoiding all that and just leaning directly into the native Linux ALSA sound architecture, this implementation becomes incredibly reliable and honestly refreshingly easy to debug. If something breaks, you know exactly which link in the chain snapped.
So to wrap up the OpenDuck, just think of it as the walkie-talkie approach, deliberate, linear state management. But wait, how does it actually remember what you just said a minute ago? Well, during this back-and-forth session, it holds the conversation context in memory by constantly appending transcriptions to a message list. That list gets sent over to the chat model every time, giving the robot its memory for that session. It's a simple setup for sure, but highly, highly effective.
Let's shift the momentum to Section 3, Mini-Pupper and real-time streaming. Here, we're trading that sequential reliability for pure concurrency, speed, and WebSockets.
Before we dive into the code for this one, I want you to think about something. How do you interrupt a talking robot? Seriously, it's a huge challenge. With that walkie-talkie approach we just talked about, if the robot is speaking, its ears are basically turned off. It literally can't hear you until it finishes its sentence. But what if you've got a super chatty AI giving you a massive paragraph of info that you just don't need? You need a way to, politely tell it to stop talking.
And that brilliantly illustrates why we need a full duplex system. Introducing a game-changer of a feature called Bargain. Bargain is exactly what it sounds like, the ability to interrupt the robot while it speaks. When the server detects human speech, the pipeline immediately triggers a function to drain the speaker queue. It instantly clears the robot's throat, stops the audio playback dead in its tracks, and forces it to listen to your new input. How cool is that?
To pull this off, the Mini-Pupper relies on an entirely different software architecture, powered by Python's Asynchronio and the OpenAI Real-Time API. Instead of sequential steps, we've got concurrent parallel loops happening at the exact same time. We have a send mic loop constantly uploading your audio, and a receive loop instantly grabbing incoming model events. Because the WebSocket logic is asynchronous, but the physical hardware callbacks are synchronous, which, yeah, is tricky, the system bridges that gap using thread-safe microphone and speaker cues. Data is just flying back and forth simultaneously.
24,000. That's the 24 kilohertz sample rate required by this real-time pipeline. To put the intense hardware demands of real-time streaming into perspective, the Mini Pupper isn't just managing this high sample rate. Its mic callback function also has to actively apply a software boost to the microphone gain just to handle the specific quirks of the robot's voice hat. And it's doing all of this while converting the signal to raw, uncompressed PCM audio data on the fly. I mean, that is an incredible amount of heavy lifting happening in real time.
So if the OpenDuck was our trusty walkie-talkie, the Mini Pupper is basically the phone call approach. It's full duplex, you get low latency, simultaneous audio capture and playback. Because you can interrupt it and it streams audio bidirectionally, this architecture feels so much closer to a natural, flowing human conversation.
Which brings us to Section 4, contrasting the two architectures. Sequential workers versus fast talkers. Let's stack them up.
Stacking these head-to-head, what's really fascinating is looking at how they handle silence and voice detection. Check this out. The OpenDuck uses a local, energy-based VAD. It literally calibrates to the room for about a second to calculate a dynamic ambient noise floor, checking the root mean square amplitude locally right on the device. But the Mini Pupper, it offloads all of that entirely to the cloud. It utilizes a semantic VAD that's handled completely server-side by OpenAI during the active session.
Furthermore, your choice of API basically dictates your entire code structure. The OpenDuck makes stateless, discrete API calls, and actually has to save the raw audio into temporary WAV files on the physical device before sending them off. The Mini Pupper, on the flip side, maintains a continuous, secure WebSocket connection. It configures the robot's persona once via a session update event, and then just streams raw audio events back and forth without saving a single file. Totally different mindsets.
Let's bring this all together. In Section 5, the architectural takeaway, it all comes down to choosing the right tool for the job. If there is one thing you take away from this entire explainer, it's this. Your software architecture absolutely must mirror your interaction goals. Neither architecture is universally better than the other. It's entirely dependent on your hardware constraints and the specific conversational vibe you want to build. Look, if you want robust, easily debuggable, simple reliability, you build a turn-based walkie-talkie pipeline. But if you need complex, natural flow with low latency and barge-in capabilities, you build a streaming WebSocket pipeline.
I'm going to leave you with this final thought. As physical AI robots become more and more integrated into our daily lives, whether as companions or assistants, which interaction paradigm do you think is going to become the standard for human-machine communication? It's a fun one to think about. I highly encourage you to go explore the open-source audio AI chat repositories, see how these pipelines are built under the hood, and maybe even start building your own voice-to-voice loops. Thanks so much for hanging out and learning with me today, and I'll see you in the next explainer.